Morning everyone, I'm Junhua Mao from UCLA. Today I'm very glad to present our work about how to generate and comprehend unambiguous object descriptions. This is a joint work from UCLA, Google, Oxford, and Johns Hopkins University. Okay, so let's discuss what is the unambiguous object description. We'll do a very simple test here. I will give you a set of descriptions, and you just need to nod your head if you know which object I'm talking about in the image. Okay, first one, a man. Okay, nobody knows what I'm talking about. Yeah, so we can add more details. A man in blue. Still no one? Okay. So what about a man in blue sweater? Yeah, I see somebody nodding his head. So actually there are just one man wearing sweater, so we know that it should be the man on the right. Okay, what about a man who is touching his head? Okay, more people was nodding his head, so this one should be a good description and it's unambiguous. Okay? So more formally, an unambiguous object description, sometimes called referring expression, is a description that uniquely describes the relevant object or region within its context so that another listener can know which object you are talking about. So this task is closely related to the task of image captioning, which is a very exciting field and lots of papers showing impressive results over the last few years. But it actually turns out to be very hard to evaluate. So for example, for the image here, I can give a description like two men sitting next to each other. So this is a perfect correct description, but many of you may think that it's too generic and can describe lots of images with totally different content. So what about we add more details? Two men are sitting next to each other in front of a desk watching something from a laptop. But still it can describe tons of images with totally different contents. In fact, there are countless details in the images, and the image captioning task itself does not define to what level we should add these details into the sentences. So, image captioning task is hard to evaluate, but it turns out to be that our referring expression task is much easier to evaluate. It turns out that there are actually two subtasks in the referring expression task. The first task is the speaker task. A speaker must take an image and a region, and he needs to produce a description for that region. So by itself, this is very similar to image captioning model. But remember that in our task, we have another task, which is a listener task. The listener task is given a description and also whole film images, and he needs to decode the description and try to identify the object that the speaker was originally want to talk about. So, and in our paper, to simplify things a bit, we have our listener always select from a finite set of candidates. Okay. So here is our baseline model. So this is a CNN and LSTM model, which is very similar to the LSTM image captioning models, except that we replace the feature extractor with the region feature extractor. It has three parts. The first part is the whole frame CNN feature extractor. The second part is the region feature extractor. And the third part is the bounding box coordinate and size feature extractor. We concatenate these three parts together and fit it into a STM model for it to decode it into a sentence. And the training objective would be the low likelihood of the sentence given the region and image. Okay. So it's actually very straightforward to apply this baseline model in the speaker module. We can simply decode the region features into using the STM with the beam search method. However, similar to image caption model, this task itself is really hard to evaluate. We will come back to this issue later. So let's then talk about listener module. So we can actually still use the trained model to calculate the probability given the sentence and the image. For example, for the description like a girl in pink, we can calculate the probability of the first regions. Probably the probability is 0.89. And we continue to calculate the probability for all the regions. And then we just pick the regions that has the highest score. And know that this task is actually very similar to object detection task, except that we replace the object class labels with the description. So we can borrow some evaluation method from the object detection, such as the precision at 1. And this gives us a pretty objective evaluations for the lesson model. And we can actually also use these models to like evaluate our speaker model in an end-to-end way. More specifically, we use the generated descriptions from the speaker module and feed it into the lesson module and use the same precision as one to evaluate the system. Okay. Okay, so let's rewrite our baseline model. So this model will focus on the ground truth regions and try to maximize the probability of the sentence given this region. So it's totally possible that this model will generate some description like a smiling girl, which is a perfectly fine description for the region, but from a listener perspective, it's actually ambiguous because there's actually another girl that is smiling in the image. So to be a better communicator, a model should consider the listener and try to think about how the listener interprets the generated sentences. And in practice, what this means is that a successful model should consider all possible regions and try to maximize the gap between the probability of the sentence given the true region and the probability of the sentence given the negative region. In other words, we want the sentence to be really good for the true region, but really bad for all the other regions. So here is our baseline model. We clone the LSTM model into several shared weight LSTM and feed all the regions into the model. So we also design some training objectives such as the softmax training loss, which will try to maximize the probability of the sentence given the true region while suppressing the probability of the sentence given the negative region. And in practice, we find that we can simplify the training by sampling the negative regions and using a max margin loss. It will achieve very similar result with the softmax version, but makes the training much easier. So to make the training of our big neural network possible, we also construct a large-scale dataset based on the Microsoft COCO dataset. To make sure that all the descriptions in this dataset are unambiguous, we conduct two-stage annotations. In the first stage, we ask a set of annotators to play the role of speaker and let them try their best to give an unambiguous description. And in the second stage, we ask another set of annotators to place the role of listener and try to verify the description from the first stage. And we iterate these two processes until we get a clean version of data. And we have made our data publicly available. And if you are interested, just click the link and download it immediately. Okay. So here, let's see some listener results. So this is the image from our test set. We have a pretty complex sentence, a dark brown house with a white stripe wearing a black sandal harness. And the system doing a pretty good job. And by the way, the blue dotted rectangle means the top alternatives generated by the model. So what about this one? A white house carrying a man. Yeah, the system point to another house, and we can change another one. A dark house carrying a woman. Yeah, it points out to the first house that in our first example. So let's do something funny. We can change the order of the words, and just so for example, we have some description like woman on a dark house. And what is really remarkable is that the system really knows it's the woman instead of the house that should be identified. So here's a result from our speaker module. For our baseline model, for example, for the cat on the left, it will generate some description like a cat lying on a bed, which is good but unambiguous. Our full model will generate description like a cat lying on the left, which is unambiguous. And here's some quantitative results. So for the lesson module, our full model gave an improvement of 4% in terms of precision at 1 over the baseline model. And if we evaluate the system in an end-to-end way, which means that we feed the generated description from speaker module to the lesson module, our full model get an improvement of 2.8 over the baseline model. And we also conduct human evaluations on Emerson Mechanical Turk. So it shows that 15.9% of the sentences generated by baseline model is considered to be better or equal to the ground truth one, while our full model get a score of 20.4%, which is 4.5% over the baseline model. Okay, so I just have one simple take-home message for you. So to be a better communicator, we need to be a better listener. So this is not only true. This is not only a good life advisor, but also true if you want to train an effective vision and language models. Okay. Thank you so much for listening.